Hello and welcome to another video in the integration series from Reigate College Maths. This video is focusing on the reverse chain rule, which builds upon the integration by inspection idea from previous videos. The main thing that's different, however, is instead of thinking about integrating f of a linear function, we're generalizing this much further into two cases. One where we have a fraction with a function on the bottom and its derivative on the top, or a function with a power times by its derivative. So this idea really requires you to be able to spot how functions are linked in terms of differentiation. So to go over that again, this is a fraction where the numerator is the derivative of the denominator, or something similar. Here, we are timesing by the derivative of the bracket. The other thing that's really important with this kind of idea is noticing when it doesn't work. Because this kind of idea, these rules, aren't always going to work. In that case, we have to do another method, which we'll look at in a separate video. So let's address this first case here. We'll look at a few examples for it. So we're going to integrate 2x over x squared plus 1. So, general rule of thumb. We have a fraction. So whenever you see integration of a fraction, ask yourself the following question. What happens when I differentiate the denominator? Okay, so what happens when I differentiate the denominator? If, in this case, we get the numerator then we can do this method. If we get numerator times by a number, then we can do something similar to this method that we'll look at in a later example. If we don't get numerator, or a product of the numerator with just a number, then we have to use a different method, which we'll look at later. So let's put this kind of checklist into practice. We're integrating a fraction. What happens if we differentiate the denominator? So this bit typically you would do in your head. So the denominator is x squared plus 1. If we differentiate that, we get 2x. Is that the numerator? Yes, it is. In this case, this is going to integrate to ln of the denominator. So in this case, we have exactly the numerator, which means our answer is ln of modulus the denominator. Now with this particular example, we don't actually need the modulus signs because x squared plus 1 always positive. So, but you won't lose marks if you put them there. So in this case, we get exactly the numerator, which means we get ln of the denominator. Let's look at another example where that doesn't happen. So, integrating cos x over sin x. So again, what happens if we differentiate the denominator? We get cos x, which is the numerator. Which means this integrates to ln of the denominator. For the more perceptive among you, you would have seen, or you may have noticed, that this is cot x. This is how you integrate cot x. But what if this doesn't work? What if we have this second option here? We get the numerator times by a number. So integrating x squared over x cubed plus 4. So let's use our checklist again. We are integrating a fraction. So what happens if we differentiate the denominator? So if we differentiate this, we get 3x squared. Now this is not the numerator, but we can see here, in this case, it's 3 times the numerator. So what we need to think of is how do we get from this to this? We times by a third. So this then integrates to ln of the denominator times by a third. So, going back to our checklist, if we get that it's the numerator times a, where a is some number, we are going to integrate to 1 over a times ln of the denominator. If it's not the numerator, if we don't get the numerator at all, and we can't multiply or divide the derivative here by a number to get the numerator, it doesn't work. It's not necessarily a log. We've got to do something else. But these two rules are really important. So let's look at one final example just to really cement that. Integrating e to the 2x over e to the 2x plus 3. So again, what I'm going to do now is in orange, I'm going to write down what you should be doing in your head. So like before, what happens if we differentiate the denominator? Well, e to the 2x differentiates to 2e to the 2x, plus 3 differentiates to 0. So it's 2e to the 2x. This is not the denominator. but it's 2 times the denominator. So how do we get from here to the denominator? We times by 1/2. So all of that you should be doing in your head. The final answer, and this is like we were doing in previous videos with the by inspection method, where you should really just be spotting it. Our final answer is that it's 1/2 ln e to the 2x plus 3 plus c. So as you get more confident with these, you can start doing this orange bit here in your head, and then just writing what I've written in green here. If you start doing that and find you start getting them wrong, go back using this until you can get them right. So that's the first case where we are integrating a fraction. Let's have a look now at when we're integrating a product. So this is our first example here, so let's have a look at it in detail. So we've got 3 cos x sine squared x, and we're integrating that with respect to x. So let's write this more helpfully just so we can see what's going on. 3 cos x sine x squared. So we can now see we have a bracket with a power, and we're timesing it by a function. So let's have a look. What happens when we differentiate the bracket? In this case, we get exactly what's on the front. So this means that this is going to integrate following our usual kind of by inspection idea. Increase the power by 1, divide by the new power. So this is exactly what's on the front. So the integral of 3 cos x sine squared x. So we take the bracket, we're going to increase the power by 1, so sine cubed x, 3 stays there, and then we divide by the new power. So it's a similar idea to what we previously looked at with the fractions. If we get exactly the extra bit, we don't need to change a huge amount. Is if we don't get exactly the not bracket bit, or in the other case, exactly the numerator, we have to think about changing things. If you're worried, double check. Do this, differentiate this using the chain rule, and you should find we get back to here. Multiply by the power, 3. Reduce the power by 1, sine squared, times by the derivative of the bracket, cos. This works. One more example. We're integrating x squared plus 5 all cubed. So again, like we did before and with the fractions, let's think about what happens if we differentiate the bracket. So the derivative of x squared plus 5 is 2x. This is not exactly what's on the front. But, like before, let's think how do we get from there to there? We times by a half. So we're going to, now we've got this idea, we're going to follow our normal rule. We're going to ignore the fact that it's x on the front, and we're going to go, okay, I'm going to increase the power by 1, divide by the new power. Then I'm going to times by this number here, and then add c on the end. So this is an 8th x squared plus 5 to the 4 plus c. Again, if you're panicky, let's check using the chain rule. We differentiate this. We're going to multiply by the power. So we're going to multiply by the power, reduce the power by 1, and then times by the derivative of the bracket. 4 times 2 times an 8 is x, or times 2x. And we can see that's what we wanted. This is one of the hardest things to do with integration, and this is one of the reasons why students find integration particularly difficult as a topic. It's also, because it's hard, very difficult to motivate yourself to practice. But that's the only way you get better, is grinding through these questions until you can just do them. Really, this here, for this example, that's what I'd expect to see as an answer. Maybe even just jumping straight to this step here. None of this working, none of these arrows kicking around up here, just this. That's what makes it difficult. So, your teachers will know that this is hard. They will appreciate that it is difficult, but they will expect you to practice until you don't find it difficult. And if you get stuck, make sure you ask them for help. Thanks for watching.